So thank you very much for the invitation, for the opportunity to be here, and definitely for the opportunity to talk to this expert audience that we have here. Rohde & Schwarz is in test and measurement since a little bit more than 90 years now. So sorry, Sami, we cannot counter your 100, but we're very, very close, and we're very much collaborating with Viavi on the topics of NTN and on 6G. Rohde & Schwarz is since more than 30 years one of the leaders in wireless technology. We started with 2G. Shortly after that, I joined the company, so I think I'm getting old there. But we've always been the reference for independent testing, and that's something that's very important to us because it eliminates the uncertainty of interoperability testing when you test a device versus an infrastructure, and in the end, it's not clear who is right, who is wrong, who's the golden standard, and who is not. So, in this presentation, I'd like to talk to you about 6G. And 6G aims to be an AI native network, enabling enhanced applications and use cases that really make it an intelligent, sustainable, adaptable, and inclusive network. And in the presentation, I will outline the latest proceedings in test and measurement and show you how we are on the way to an AI native air interface, ensuring a safer and connected world. So let's have a quick look at the timeline. You've seen that many times before, and I will not go into too much details. One or two important, I think, data points there is certainly the 6G Pre-Vision Fest in 2026, that's planned for Korea. The 6G Vision Fest in 2028, where we expect to see maybe some pre-commercial implementations of 6G networks. And this falls very nicely in line with also the Summer Olympics in the US in 2028, when other network operators like Verizon announced also to have first network functionality available. And we also see chipset vendors and device vendors targeting 2028 as the initial first prototype phase for 6G. These are all the applications that we see, the technology applications that we see as relevant for 6G, and this is quite a lot. We started up in the corner with FR3, and you showed that on the slide before, and maybe I'll quickly go back to that. Sorry for that. So you see on the very left corner, there's the frequency spectrum that's currently under discussion. You see the World Radio Conference 2027 dealing with the frequency range up to 8.4, and then something in the 15 gigahertz space. The US government pretty much notched out the 7.4 to 8.4, so a lot of focus right now is on 6.4 to 7.125 gigahertz frequency range. And that's also the focus, the focus of the frequency extension right now, the so-called FR3 frequency range. Probably after 2030, we would also see activities in 15 gigahertz, but there seems to be a huge concern going up and beyond 10 gigahertz, because this would definitely mean a lot of more OTA testing. So look, that's the frequency aspect. The next one is integrated sensing and communication. We heard already also from Sami that this is a very hot topic, getting a kind of, it used to be called tactile internet, or getting this immersive experience, tracking objects like ships, like drones, like cars, tracking people, tracking gatherings of people. There are lots of applications in ISAC, and I think with 6G we have the opportunity to use the communication technology to have basically a global also sensor network for detection. I just quickly jump over AI and go to the very right corner with the extended reality and metaverse, and that's one of the important applications where we expect it will drive data consumption again. That's where we heard yesterday in one of the presentations talking about 30% data growth. I think it's probably going to be more like 20% for the next 5 years. But this is where a lot of this data growth will come from people using smart glasses with cameras, cameras that monitor the environment, that send this data up to the edge, and then a assisted AI interface will basically tell these customers, okay, what's the tower that I'm seeing there? Oh yeah, that's Taipei 101. Tell me about Taipei 101. What is the best tour there? When can I get a tour guide? What's the bus transportation? And this is where AI actually will come in. A lot of the AI on-run applications will be these agentic services, making life easier for the user, basically being your personal assistant in a digital format. So AI and metaverse and XR are very closely related. Other one is reconfigurable intelligent surfaces. We have a very nice demo at our booth showing a 5.5 gigahertz RIS. Please come down to see that. This is something, FR2 kind of didn't make it to the market because of the issues with signal propagation, that our millimeter waves just do not go around corners. They just go straight. And so you have really a big coverage problem, and RIS is hopefully going to resolve that for FR3 and for the higher frequencies that we are looking at. On the lower side, we have lots of other things. NTN was already mentioned by Sami. I mean, that's something that probably most of us are using already. I mean, everyone who has an iPhone 14 or one of the newer devices, they support either proprietary or narrowband IoT NTN versions already. And this is going to keep us busy for the next coming years. And other things, obviously, like massive MIMO. Full duplex is something that's very much related also to ISAC, because it's actually needed for that. So let's have a look a little bit on the AI run and how, or on the AI technology, because this impacts each and every one of those technology blocks. And I like to give at this point a very big thank you to the AI RAN Alliance for giving a little bit structure to our train of thoughts. Looking at AI and how this was really kind of hyped over the last couple of years, I have to say, I don't know how many of you have children, but to me it felt like a children birthday party. And after the birthday party, you look into the room and there's all kinds of stuff on the floor. And you just feel, okay, shit, how do I get structure into this? How do I sort that? And I think the AI Alliance did a fantastic job of putting structure to our thoughts about AI, separating AI applications into the AI on-RAN box, separating AI for RAN for all the topics that optimize the network, and then finally AI and RAN for the shared infrastructure. And it's really helpful because now we know exactly what we're talking about. So let's have a deeper look into the AI for RAN, because that's the one where Rohde and Schwarz is most active. We have a couple of activities in 3GPP since a couple of years already. So starting with SA1 with model transfer, dealing on that since a while. We had SA2 dealing with support for AI/ML-based services, SA4 with media, SA5 dealing with AI/ML management. And then finally now we have the big activity for AI/ML on the air interface, which will deal with the pilot use cases starting from release 18. And then also, and that's most important, to qualify the gain that AI can actually bring. Because we're not doing AI for the sake of doing AI, we're doing AI because it shall bring us real advantages in the network operations. And also finally, what this means to specification and how that can be tested. On the bottom of that slide, I have the three, let's say, topologies of AI. Obviously, you can have AI just in the device, you can have it in the network, or you can have these two-sided models where the network and the device actually collaborate and they exchange models, they exchange data, they jointly optimize performance. And this is actually where Rohde and Schwarz is very, very active, and that's the most interesting part for us, because that means changes in the testing methodology. And as said, we like to continue to be the reference for that. So let's have a look at these two-sided models specifically. As I said, 3GPP started working on this with release 18. There were initially 3 use cases or pilot use cases identified. One is the CSI compression. CSI is the channel state information that basically means the mobile is transmitting information about how it receives the base station signal back into the base station, and the infrastructure uses this information to optimize its beamforming and the massive MIMO schemes. This is a lot of data that's collected by the user equipment. So 3GPP already took caution to compress this data. So there are some standard methods for compression, but we think that we can improve this even further. The other use case here is the beam management, quite closely related, and the last one is positioning accuracy enhancements. So out of these three, these sub-team topics here made it into work items for release 19. That's positioning accuracy, beam management, and on the CSI, it's just a prediction. They didn't, in the first step, consider the compression because the compression actually requires a two-sided model, and there were basically three concerns. One was, does it really provide gain in the field? And is it really testable, these two-sided models? We addressed those concerns together with Qualcomm, and I'd like to show you a little bit how we did that. Yeah, and finally, these results with Qualcomm, the work with Qualcomm resulted in also CSI compression becoming a work item now in release 20, but still in the 5G specification realm. So I have here a quick video from Qualcomm, and let them speak to it by themselves.
The CMX 5G one-box signaling tester emulates the network side of this AI-enhanced CSF setup. Rohde and Schwarz trains the decoder for the one-box signaling tester based on specified reference encoder-decoder models and test conditions. Separately, the device vendor trains a proprietary device encoder based on specified reference encoder-decoder models and test conditions. The decoder at the CMX 500 5G one-box tester signaling tester and the proprietary device encoder are interoperable because both have been trained to be compatible with specified reference models. With the training completed, it's time for some performance testing. As seen in our test, the AI-enhanced CSF can achieve significantly better throughput compared to traditional design that does not support wireless AI. In conclusion, the AI-enhanced CSF we have demonstrated today is not only delivering meaningful gains, but they can also be robustly maintained and tested.
Yes. Thank you very much to Qualcomm for recording this video for us. I think it's very impressive proof that this actually achieved the three concerns or addressed the three concerns. One was gain, the other one was can we get models on there, and the second one is interoperability testing. Just looking a little bit more on how this looks like, you see here also that's the summary slide we have on the CSI feedback compression that we showed a couple of times. As said, we achieved meaningful throughput, more than 50%. Now, I wouldn't put my hand into fire that this 50% will be achieved in real life. That's a specific use case, specific fading model. We were comparing it against a type 1B standard model. We've checked in the meantime also newer proceedings of the standard reference encoders in 3GPP, and we were able to actually maintain that gain. So it seems to be that it's really a consistent gain that we can achieve by using these models. The other thing that was very important is on our CMX Radiocom tester, you see this small little brain up there. This means that we implemented a standard interface, so-called ONNX, Open Neural Network Exchange, that allows also customers to bring in their reference model over a standardized interface into our Radiocom tester, that you're actually able to test this against user equipment. So that's the model portability. And finally, we showed the testability. The way we did that is we trained first internally with our own neural receiver against the encoder against the decoder. We transferred our decoder to Qualcomm. They learned it against their implementation. And finally, we had the two models running against each other with a very successful result, as I showed. And yeah, that's the final setup that we had at Mobile World Congress beginning of this year. So as said, 3GPP was convinced. They started the work item for release 20. So they will explicitly look now at AI/ML two-sided models. They will look at what this means in terms of training and collaboration of the two sites and also at interoperability. And all that is already is 5G, but it's on the way into 6G. Some final information on that, on the testing models. There are some ideas being discussed. One is to have a complete reference model. The other one would be to standardize just the data. But even though Viavi has great access to data, not everybody in the world has that. So currently the idea of having standardized data sets is a little bit prioritized down. And we are looking more at the three options there below, probably getting 3GPP to standardize a reference model that we could load on our tester. That would be the basis for testing against customer models on the user equipment side. Looking now a little bit into the infrastructure and the neural receivers and what could be done to test G-Node Bs and receivers. We've done a lot of work with NVIDIA over the last years on basically combining demodulation, demapping, channel equalization and channel estimation into one neural receiver block. We worked on their Siona engine and provided them with means of test to verify how that works really in an RF environment. What we did there and what we showed on a couple of exhibitions is we used one of our signal generators, the SMW, to generate two pieces of user equipment, both with 2x2 MIMO. We added the channel impairments and channel propagation conditions in the box, digitized this with a standard receiver, put this into our server-based testing software to demap the information, and finally we put the constellation diagram into the neural receiver from Siona, and they were able to process that. And based on that, we could show the performance of their neural receiver versus 3GPP standard receivers. But what we are recently adding is we're now also looking at the modulation part into custom constellations. And this is something that is getting very interesting. I mean, generally, why do we think that AI-based receivers actually create a gain over standard receivers? This is the way we have to look a little bit back in how standardization has been working for the last years. Basically, with every new generation, people went out in the field, they did complex channel sounding campaigns to assess how the signal propagates in certain frequency ranges. This was for a long time really, we had good models up to 3 gigahertz, then now up to 6 gigahertz, and even up to higher frequencies. But all the time, all this massive amount of data was compressed down into a handful of fading models that made it then into the test specification in RAN 5. So all the devices are testing against a handful of fading models, which are a stochastic approximation of the world put into 10 different boxes. Obviously, now you can imagine that if I look at this auditorium here, that this is probably not 100% reflected in one of those 10 boxes for propagation. And if you really look at how the signal propagates in this auditorium, you could do better in your radio signal. And that's the whole idea behind this IML. This has impacts on the channel equalizer and things like that, but you can also tune your modulation to fit better to this propagation condition. And I'd like to show you what we did there. Yep, there we go. So we again did some simulations where we actually changed the constellation diagram. We went from the square constellation diagram that you usually have to a non-square one. We still kept the number of constellation points, but we just put them in a different order. And we saw already by doing this some gain on the equalizer and on the demapping that you see here up in the diagram. Sometimes it's always 3 dB. I have no idea why this is. This 3 dB seems to be a constant. If you do these kind of trials that you show improvements, it's always 3 dB. 3 or 6, but in this case it's 3. So this is what we did here. And the other thing is, now you see this constellation diagram down here in the corner, and it's really uneven. And you see this one point sticking out there on the upper left corner. And the nice thing is, because of that, the constellation diagram has its own built-in pilot symbol. So we can eliminate the pilot symbols, and again, we get more capacity on the radio channel because we don't need to transmit the pilot symbols anymore. We have pilotless operation. And again, this is another gain on top of these 3 dB that we showed there. Obviously, again, this is research, so we are evaluating certain conditions. We need to retrain the models if we change the fading parameters, if we change the propagation conditions. And in the end, it needs to match the field experience and have ground truth there. But it shows that it's a potential where we can reap some dB in order to make 6G rollout more successful. And this is a real demo of how we are actually implementing this in our equipment. You see here one of the, again, the same signal generator, SMW200, transmitting an 8 gigahertz signal with 500 megahertz, initially with a 4K QAM modulation. And in this video, we're first reducing this down to 1K QAM, because I'm personally getting old. I can't resolve all those little dots anymore, so I need bigger dots. So we're going to 1K QAM, and then we're showing you what the ideal constellation diagram would look like in the future on a 1K QAM modulation, just in a second. And then we will show it here. So just switching on the custom modulation. And I just sincerely hope that this will be the really perfect diagram for the future. Sorry, probably not, but I'm still looking for the ideal environment where that would actually mean a 3 dB gain. Having said that, and talking about propagation and simulating real life, a big topic is ray tracing, and we heard that already from Same. Viavi is doing a lot of activities. We're doing lots of activities initially with NVIDIA. This is something we also showed beginning of this year on Mobile World Congress. NVIDIA did a ray tracing simulation of our campus. We, let's say, sharpened this a little bit by bringing in the exact building configuration and things like that. And then we ran a channel sounding campaign in our campus to calibrate their algorithms. And that made it easier to kind of consider basically the dielectric constants of the buildings. You know, you have glass, metal, concrete. They have quite different reflectivity and so on. And we just compensated by doing channel sounding in our environment. And we were able to, oops, oh, sorry, I'm on the wrong slide. Sorry. Sorry, I meant to show that one. And you see this slight uplift there, this colored area. The initial values from NVIDIA were the deep ones, and we managed to move that up there to realistic values. And we did not only do this with NVIDIA, we also have a very nice proof of concept with ANSYS. Again, ANSYS is doing ray tracing emulations, simulating environment. You see up there the downtown of Denver. And you see basically two objects moving there around the street. You see a base station up on the roof. The ANSYS RF channel modeler calculates the channel impulse response that each of those objects would see of the signals coming from the base station. This channel impulse response goes into a data file. We can load it into the SMW signal generator. And so the signal generator replays a base station signal, and the RF signal can be used to train and measure user equipment. Down there on the scope, you actually see the channel impulse response. So the objects are just crossing the base stations. This is why the delay went a little bit closer. Now the delay is spreading out again, and you see also these additional spikes there. This is the channel impulse response as calculated and as simulated by our signal generator. So it's a great way to bring field simulation into the lab with our equipment, and to verify and train performance of AI-enabled user equipment. That's a summary. These are the 4 or 5 demos we did with NVIDIA and ANSYS, and it's just a summary of the slide over time. So let's have a look at the very latest proceedings, what we did, and this is called digital post-distortion. This is something that we analyzed as part of a German research project, 6G-ANA, together with Fraunhofer, with Ericsson, with many, many other partners. And the idea is basically, I mean, if you look at the 5G frequency range that's being looked at, going back to the very beginning of the presentation, we're looking at 6 to 7 gigahertz. The free space path loss at 6 to 7 gigahertz is about 6 dB less than at 3.5. And that is a problem because the network operators obviously like to keep their existing cell sites, to keep the cell grid. So most of any of the applications that are being done also in neural receivers and anything, they target keeping up the cell edge performance or to improve the cell edge performance. And so also this digital post distortion is one of the possible measures to get more power to the cell edge. If a mobile is really at the cell edge at the end of its reference sensitivity, what can we do to get a good performance still at this edge? And one very simple idea is obviously, okay, let's turn up the power. I mean, US companies, the first thing, why do you have high powers, high power? And the same thing on the user equipment, just give it a little bit of power. Okay, what happens if you apply more power is obviously you get a distorted signal. So in a normal network, this wouldn't gain you anything because you would just simply crash the signal quality. So the digital post distortion is now a method with an AI-based receiver to remove this distortion in the base station. So when the harm is already done. So the mobile does harm, but the base station removes it. So it's a very attractive use case, obviously, for base station vendors to position themselves in 6G. And this is what we did initially in 6G ANA, and we just enhanced that together with Nokia. We're starting a work item in the AI-RAN Alliance on that topic next week, actually in the Boston meeting. So, and these are the results. Sorry, these are the results that we achieved in the 6G ANA project. So you see, we were able to move the curve to the right. And improve the bit error rate quite significantly. Obviously, again, that's a proof of concept. That's just one data point in the whole realm, in the whole plasma of possible parameters, but it shows there is a potential for gain, and let's work on that to see if that helps us to improve AI, RAN, and 6G implementation. And having said that, I'd like to come to the takeaways and to the end of my presentation. We showed that a lot of work is already done in 5G with release 18 to release 20, taking on some of the challenges of AI RAN by defining test methodologies, by defining interoperability testing, by taking care of lifecycle management of AI models. The next step, or the important one for us and the most interesting one for us, are these two-sided models that we showed with the CSI compression, that these are testable, that they have gains, and that we can manage these models in real life. And we intend to remain the reference in testing for interoperability testing and be hopefully a very important cornerstone to make 6G successful. And with that, I'd like to thank you for listening to the presentation. And I wish you a successful rest of this Congress. Thank you very much.